morning, Trig fans. How we doing on this fine Monday morning? I hope your weekend went really well. Hope you stayed warm. It was chilly out there. Chilly today still. Tomorrow they say it's going to start warming up and we're going to be into some nice warm weather. So hopefully we will be there. But right now it's sort of yucky. Gives you no excuses not to get your homework done now. Right? You can keep up with the material. You have nothing else better to do. You can't go outside really because it's not very nice to go outside. So get your work done. You guys have been doing a very good job of completing what you need to complete. I've posted and I got everything graded and back to you that I've got so far. As a couple of you still are missing a couple things, please get them taken care of. We have 2 more topics to cover. 2 more. We're going to breeze through vectors today. Victor, we'll work on this today and also tomorrow. Wednesday will be once again the review day. Thursday will be the evaluation. Thursday and Friday will be the evaluation. And then next week we'll go over some polar coordinates, a couple days of polar coordinates, and that will be it. That will be it. So there'll be nothing else that will be there. So we have vectors to deal with today and this week, and we have polar coordinates next week, and then we will be done. We'll be done, and hopefully once again the weather will be nice enough, and we'll be able to get outside then and enjoy some nice weather. Today we're going to start dealing with vectors. Victor, what is the idea of a vector? What is a vector? Well, if I was starting at the flagpole, and typically I have students do this also, starting at the flagpole, write the directions to your house with specific length and specific direction. So if you're standing outside in a car or sitting outside in a car and you're going to drive to your house and you're going to give directions to your house, okay? I'm not saying to sit there and type in an address into your phone and sit there and say, let the phone tell you how to get to your house. I want you to tell me how you get to your house, okay? And you have to give a specific length and a specific direction. For example, if you were going to my house, you would start out the flagpole, drive, that's about 100 yards south, because that is the direction of south. And it's about the length of a football field where we're at here compared to the end down by Mrs. Ed's room. That's about 100 yards, and we're going south. Need to go length and also direction. We're going to turn and go left, so I'm going to go east. So we're going to turn left and travel, let's see, that would be about 25 yards. And that would be east because I'm going in next direction. That's where the sun is coming up. So it's 25 yards east, and that will take me to the stop sign out there. Okay, I'm going to turn left again, and I'm going to drive 2/10 of a mile north. Once again, 2/10 of a mile. I'm just going to go 2/10 of a mile in that direction that way. Okay, and it might be a quarter of a mile, 0.25, somewhere in that range. It's going to be close enough to about 2/10 or about a quarter of a mile, 0.25 of a mile, that direction. And then I'm going to go turn left one more time, and we're going to travel 0.25 miles, and we're going to go west because we're going to turn and go in that direction. And then you'll arrive at my house. Okay, this here, and we just bulleted these, are directions to our house. Before the advent of this, and you can sit there and go, okay, how do I get to my house? My location, I could type in an address and get to my house that way. Before we had that, we had to do something called a map quest. A map quest was a bullet by bullet direction to get to from one place to another, and I still use MapQuest because I like to go that direction. I like to be able to figure things out a little bit more. It helps my brain stay sharp. But before that, you called up on the phone or you looked at a map and said, okay, I had to drive this direction, I have to go on this road to this road to this road to this road, and I could get to a house. Okay, we didn't have phones back even 25 years ago to be able to get from one place to another. You had to figure it out. Okay, you had to figure it out to get from one place to another. So the phones have really, I'm sorry to say it, dummied us down a little bit, because we could type in an address and it tells us, it even talks to us. Whatever language we want, whatever accent we want, it talks to us and tells us to get over in this lane or get over in this lane, rather than looking at the signs and trying to figure it out. Well, each one of these right here are vectors. They are vectors. Each bullet is a vector. Because the definition of a vector that we have, it is a directed segment. A directed segment. A segment, you have two endpoints. You learned that down in Dr. Clark's class. When you have a segment, you have not a line that doesn't go on indefinitely. You have a starting spot and you have an ending spot, and you have a segment. We could put a ruler to it. You can measure it. Okay, you have a definite length. And a directed segment is telling us the direction that we have to go. If I had these directions here and you were starting down there to double D, and I said, follow these directions to get to my house, would you get to my house? No, you wouldn't. Okay? No, you wouldn't. You have to have different directions then at that point. So it is a segment with specific length and specific direction. A segment with specific length and specific direction. Now once again, if I'm going too fast, just hit your pause button. Okay, you have a specific length and specific direction. You have to have an initial position. It's the starting position of a vector. It's where you start. I had to tell you we're starting at the flagpole. That was the starting position. Once again, if I gave you a different starting position, going 0.2 of a mile south or 100 yards south is not going to get you started to go into my house. This is also called the tail. Okay, this is also called the tail, the initial position. We also have the terminal position. It's the ending position of a vector, also called the tip. Okay, it's where you end. These positions are the endpoints to the segment. Okay, these are the endpoints of the segment. Okay, vectors, a directed segment, you have to have two endpoints. These are the two endpoints of that segment. It tells us where we start and where we stop. So if I have an initial position, and then here's my terminal position, I can draw a segment between them. Now, that tells me a specific length. How do I know which direction it's going? How do I know? How do I know this is initial and this is terminal with me not giving those as initial and terminal? Well, what we do is we put an arrow. We put an arrow, and I put a half arrow. Now, some books will tell you you put a full arrow, and bold-face it. Other books will be a half arrow. I like the half arrow. The reason why is what you have learned throughout your math career is if you had something that looked like this in geometry, what'd you call this? That's correct, you call it a ray. And by definition, a ray continues on indefinitely. It has a starting spot, but it continues on indefinitely in a specific direction. Well, with a vector, Victor, we don't continue on indefinitely. We don't go indefinitely in a specific direction. A ray does. So that's why I like to use the half arrow there. So we have the initial position, we have a terminal position. And once again, this is called the tip. This is called the tail. You label with a lowercase letter with a vector symbol above it. So we can label this any lowercase letter. I'll go V, and we put a little arrow above it, a vector above it, Victor. So this is vector V. If I wanted to use vector A, that would have been fine. If I would only use vector X, that is fine. Any lowercase letter will work. The magnitude. When we talk about the magnitude, it is the length of the vector. Victor? The length of it. How long is it? So it's basically with no direction. It's just how long did you go? How far did you go in each length? A scalar multiplier. It's a coefficient of a vector that affects the magnitude, which is the length, but not the direction. And we'll talk about this on the other side when we start drawing. Okay, so it's a coefficient to the vector that affects the magnitude of it, the length of it, but not the direction. That is a scalar multiplier. And the last thing we will deal with is what is called a resultant vector. Victor? It is the solution to a vector addition problem. What's the solution? Well, what is the result? Well, it's called the resultant vector. Victor? And how we symbolize this is we put a little subscript R there. This is your resultant vector. Victor? So these are some very basic definitions and basic terms of dealing with vectors. Victor? And once again, if I'm going too fast, I will not take offense if you hit your pause button. Okay? And you'll get some practice with drawing these today. Today's homework is going to be not like we typically have done. I'm going to give you actual worksheet to deal with and some solutions that you can check your solutions with because you're going to be dealing with some drawing. I felt this was a little bit better and we'll continue with this throughout the rest then. Go on the back. Here I have two vectors. Victor? This is vector A, this is vector B. Now when we are drawing these, you want to try to maintain a specific length. You want to put a straight edge up to it, and here's my length that I want with this here. I want to be able to use that exact same length. What I do, and you don't have the capability of doing this, is cloning it. What I've always suggested, you can use your straight edge. Once again, I like straight edges. Straight lines are made with straight edges. Make your Mr. Wizard straight edge and then put a line here and a line here and say, okay, that is the length of vector A. And then here to here, this is the length of vector B. So you have the actual length. You can hold your paper up here and say, okay, this is my vector A, and then this is the length of vector B. I'll clone them here. So if I have 2A, this is a scalar multiplier. 2 times A. I want 2 of the A's. Well, this is 1 of the A's, but but I want 2 of them. So I'm going to clone this again, maybe. Yeah. There we go. And drag this up to here. And this is another A, or this would be 2A. I've just doubled the length. I didn't change any of the direction. I just, rather than going 100 yards, I've gone 200 yards. Rather than going 1 mile, I've gone 2 miles. I just doubled the length. Negative 3b. Negative 3b. Well, we need 3 of the b's, but I wonder what this negative does. Well, the negative in the math world means the opposite. So we have to go to, once again, SpongeBob opposite day. Okay, SpongeBob opposite day. If I'm looking at B, clone it. Let's bring it down here. This would be just B. But what would be the opposite to B? What do you think we should do to get the opposite of B? That's correct. Rather than going 10 yards that way, I'm going to go 10 yards that way. We go the opposite direction. So when I throw that negative in there, the arrow just comes down to this side. It goes the opposite way. Because that's what a negative means. It means the opposite. And I want 3 of them. So there's 2, and then there's 3. This would be negative 3b. Well, what if I asked to add a plus b? Well, when I was giving directions on this side, we were dealing with vector addition. Okay, this here was vector addition because I went from the flagpole here to the end of the building by Mrs. Edgerum. That was my first vector. Then I stopped and I turned left and went that way. So wherever I stopped this, I started the second one. Okay, wherever I stopped the second one, I started the third one. Okay, there was no Starship Enterprise up in the sky that we can pull out our tricorder and say, beam me up, Scotty, okay? And then he would beam me up to the Starship Enterprise and then beam me down to a different place, okay? Wherever I stopped one, I started the second one. That was vector addition, Victor. So this tells me to travel vector A first. So I'm just going to pull this one down, maybe. This was vector A. I traveled, I started here, and I could start this at any spot. I could pick any spot I wanted to. This is my initial position. This is my terminal position. Wherever I stop at, I'm going to start the second one. So I'm going to travel B. So I'm going to pull this one down, clone. And I'm going to travel B. So I'm traveling A first. Wherever I stopped the first one, I started the second one. It's what sometimes is called tail to tip. You put the tail of the second to the tip of the first. And I draw A plus B. But the problem we run into, if you were given this test and you said 5 plus 4 and it has an equal sign there, what would you write in there in the blank? That's correct. You would write in the value of 9 because that is the result to 5 plus 4. Well, would this have been true? Yeah, 5 plus 4 does equal 5 plus 4. Well, if I ask you to draw A plus B, and you just draw this and you leave it alone, what you have done is you said 5 plus 4 is equal to 5 plus 4. we have to give a result. Well, how do I find a result? I have no numbers there. How do I find a result? Well, we get to go back to our fond memories of Little Red Riding Hood. Yes, we all remember the story of Little Red Riding Hood. Little Red Riding Hood was going to Grandma's house. So Little Red Riding Hood's going la 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 la, or it's going here la 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 la, and at some point, Little Red Riding Hood met up with the Big Bad Wolf. So at this point right here, we hit the Big Bad Wolf. And we still want to get to Grandma's house over here. Well, Little Red Riding Hood stopped by Big Bad Wolf. Big Bad Wolf said, "Where you going, Little Red Riding Hood?" "I'm going to Grandma's house." "All right." And the Big Bad Wolf said, "Oh, what you got in the basket there, Little Red Riding Hood?" And we all know the rest of the story at that point. Well, Little Red Riding Hood went on her way. So she continued down the path to Grandma's house. But we also know the Big Bad Wolf took the shortcut to Grandma's house. Well, the shortcut is the shortest distance between 2 points. So the Big Bad Wolf went this way to Grandma's house. Because that was a shortcut. What we just drew in there is what we call the resultant vector. Victor? It is the shortcut to Grandma's house. So we'll do 2 more here. If we had A minus B. Well, this was vector addition. This says vector subtraction. How do we subtract them? Well, we go and do a little boom chain. So we put a negative up there. We make this a positive, make that a negative. Which means we're now still dealing with vector addition, but we're adding a negative B. So we are going to travel A first. Pull A down from here, maybe. We're going to still travel A first. Maybe. There we go. So we're still traveling A first. But now we're going the negative B. Well, what we learned up here, that's a SpongeBob opposite day. So we go negative B. Rather than going upwards to the right, because that would be plus B, we have to go in the opposite direction, negative B. And then we draw in our resultant vector. Victor. So that would be our resultant vector. If we have A plus 2B, once again, we're going to go A. We're going to go A first, maybe. There we go. We're going to travel A first, and then we're going to go 2 of the B's. So I'm going to clone 2 of them. Here is my A. Here is 1B. Wherever I stop that, I'm going to throw my second. I just double my length. Here's another B, so this would be 2B. And then I draw in my resultant vector. Victor. So here's my resultant vector. Victor. If we throw numbers to this, I got two vectors here, A and B. I want to calculate the magnitude of A plus B, which is the magnitude of the resultant vector. How we signify magnitude is a double absolute value sign. You can do single absolute value signs. It depends on what book you look at. First, we need to draw A plus B. We have A is the length of 8, B is the length of 10. So I want to draw the picture A plus B. Well, both of these are connected at the tails. It's sort of like a cat-dog thing going on here. Okay, so we connect them at the tails. I need to first draw in A plus B. Well, if I draw in A, here's my A, and then I need to add B to that. So wherever I stop A, I need to start B. So there is A plus B. A has a length of 8 and B has a length of 10. And what I want to find is what is the result of A plus B. Well, A plus B, you might say A plus 10 is 18. No, we want the result of that. So if I draw in my resultant vector, this is my resultant vector. This is what I want to find the length of. Well, what I've just created is a triangle. And in this triangle, I know two sides. I want to find the third side. Well, what we just learned in the past section was the law of cosines. If I know two of the sides, I need to find the third side. I need to also know an angle. Well, if I take a look at my angle here, I'm given an angle, but this doesn't look like the same angle. So if I would draw or drag B up, what we would have is we would continue with this 40 degrees as we go up. As we go up. Well, when we get to the final tip of this, this is your 40 degrees. What's the angle within the triangle? Well, these are what is called a linear pair. And if you remember back to your fond memories of geometry, all linear pair, if you have a pair of angles that the backside form a line, their angles will be supplementary. So if this is 40, this would be 140 degrees. So this would be 140 degrees. So what I now have is I have two sides and the included angle. I want to find the third side. Well, that takes us back to our law of cosines, where VR squared is equal to 8 squared plus 10 squared minus 2 times 8 times 10 cosine of 140 degrees. I can't find my calculator, so I guess I'd go up to my old school calculator. Now remember, this will give us, let's see, we have 8 squared plus 10 squared minus 2 times 8 times 10 cosine of 140. This gives us the square, VR squared, and then we'll have to square root our answer. So we have 16.93. We also need to get a direction here. And what I'm going to do is I'm going to just go in another variable here. I'm going to use the variable alpha. Looks like a fish. We want to find this measure of this angle here. And since this is already an obtuse angle, I can use my law of sines. The sine of alpha over 10 is equal to the sine of 140 over a value of 16.93. So to find this angle, we have 10 sine of 140 divided by 116, 16.93. That's the sine of alpha. So we have 10 sine of 140, 10 sine of 140 divided by my answer that I just had up there. We get 0.3797, and then we can do our second inverse sine of our answer and get 22.3 degrees. So my alpha value here is 22.3 degrees. If we're asking to calculate A minus B, here's our A, here's our B. We still have the 140 here, or 40. But now if we do A minus B, we're going to travel A first. And we just did plus B, which is this. What we have to do is we have to go in the opposite direction. So we have A, and this is a minus B. Now the key here, or the question is what's our angle? Well, what we had before is this one was 40 degrees. And we were going down this way. Well, if this is going 40 degrees here, we have parallel lines cut by a transversal. This angle here also has to be 40 degrees. And then we can draw in our result vector. Victor? We're going to want to, once again, use our law of cosines. Now this is still a value of 10 and this is still a value of 8. Okay, this is not a negative 10 length, it's still a length of 10. So we have VR squared is equal to 8 squared plus 10 squared minus 2 times 8 times 10 cosine of now just 40 degrees. And then we want to be able to find this alpha. Now if you don't already have an obtuse angle in there, you have to watch yourself because this is going to end up being our biggest side. You're going to have to use your law of cosines to be able to find alpha. So you're going to have to do cosine of alpha at the very end. You have to watch because that law of sines gives us two solutions there. Once again, I have posted a worksheet for you, some practice dealing with both of these things. The first part, you're just drawing the vectors in there. The second part, you're doing some calculations. I've also posted some solutions to it also. So get yourself through the material. Once again, we only have two. We have this, and tomorrow we'll get into some word problems and deal with more vector addition and the word problems. And that will be tomorrow. And then Wednesday will be a review day, and Thursday will be a quiz over this material. Please do keep up with the material. I know we're getting near the end. I get this. We're in the middle of May. I get this. But we still need to be able to keep up the material and get ourselves through it. This is the more of the difficult too. The polar coordinates next week are not very difficult to be able to get through. This is a little bit more lengthy of a process. But you should be able to handle it because eventually we're just going back and using our law of sines and cosines again. If you have any questions, feel free to contact me, email me. Tomorrow we'll come in. Once again, if you have any questions, I'll go over any problems that you have with them. We'll deal with some story problems and deal with the idea of bearing tomorrow. We'll once again be setting up law of sines and cosines problems here with the idea of bearing. please do keep up the material. You guys have been doing a very good job. Please do keep up with it. If you have questions, once again, feel free to ask. Other than that, I'm out of here. I have nothing else for the day. And tomorrow I will come in, we'll deal with some additional problems, and once again, we'll keep the process going here as we've done the last couple of weeks. Other than that, adios. I'm out of here. I miss you guys. You guys have a great day.